Every science class you ever sat in taught you the same quiet certainty. There is living matter and there is dead matter, and the two are different kinds of thing. A tree is alive. The stone beside it is not. You are alive. The chair beneath you is not. It feels less like an opinion and more like a fact built into reality. But here is what they left out. Every living thing you have ever seen is made of exactly the same atoms as that stone. Carbon, oxygen, hydrogen, nitrogen. There is no special living atom. There is no spark you could point to. Take a person apart, down to the atoms, and nothing in the pile would be out of place in a rock or the sea or the air. The difference between you and the chair is not the parts. It is only the arrangement. And that means, roughly 4 billion years ago, that arrangement happened for the first time, and dead matter did the one thing we are told it cannot do. It became alive. Get comfortable. Hit subscribe if you're new here, because by the end of this, the line between living and not living will not look like a line at all. Now, let's slowly ease into this. Part 1. The category we never question. There is a distinction you have carried with you your entire life, and you have almost certainly never once stopped to examine it. It is the difference between something that is alive and something that is not. A tree is alive. The stone it grows beside is not. A bird is alive. The fence it lands on is not. You are alive. The chair you are sitting in, or the bed you are lying on as you listen to this, is not. Of all the categories the human mind uses to sort the world, this one feels like the most secure. It feels less like an opinion and more like a fact built into reality itself. The way up is different from down. The way hot is different from cold. So let us begin there, with that certainty, because by the end of this, it will be gone. And I want you to remember how solid it felt at the start. Picture two objects sitting side by side. The first is a redwood tree, 300 feet tall, 4,000 years old, its bark thick and fibrous, its roots threaded through the soil, water moving up its trunk in a slow, continuous column. The second is a granite boulder resting in that same forest, grey and flecked and patient, formed from cooled magma 100 million years before the tree's first seed existed. Look at them. Your mind sorts them instantly and without effort. One of them belongs to the kingdom of the living. The other belongs to the kingdom of the inert, the mineral, the merely physical. You did not have to think about it. The sorting happened beneath thought, automatic, certain. But now, I want you to ask the question that almost nobody asks, because it sounds, at first, almost too simple to be worth asking. What, exactly, is the difference? Not the obvious surface difference. Not that one is brown and one is grey, that one is tall and one is round. I mean the real difference, the fundamental one. What is it, precisely, that the redwood has and the boulder lacks? What is the thing that makes one of them alive? You will find, if you sit with that question honestly, that it is much harder to answer than it has any right to be. You might say, the tree grows and the boulder does not, but crystals grow. A crystal in a saturated solution will add atom after atom to itself in a perfectly ordered pattern, expanding, taking on new material, and no one calls a crystal alive. You might say the tree responds to its environment. But so does the boulder, in its way, expanding when the sun heats it, contracting when the night cools it, slowly cracking along the lines where water has worked into it. You might say, the tree reproduces, and that is closer to something real. But it still does not tell you what the tree is, only what it does. This is the strange thing about life. We are surrounded by it. We are made of it. And yet when you try to put your finger on what it actually is, the definition keeps sliding away from you. We recognize life the way we recognize a face in a crowd, instantly, with total confidence, and with almost no ability to explain the recognition. Here is what I want you to hold on to as we go forward. The distinction between living and non-living feels absolute. It feels like a wall. On one side, the redwood, the bird, to you. On the other side, the boulder, the fence, the chair. And the entire journey of this video is going to be a slow, patient walk up to that wall, to look at it closely, to run our hands along it, and to discover something genuinely unsettling. The wall is not made of stone. It was never as solid as it looked. And the closer we get to it, the more it begins to look less like a wall and more like a mist, something you could walk straight through without ever knowing the moment you crossed. Because here is the fact that should already be making you uneasy. Every living thing you have ever seen, every creature, every plant, every microbe, every cell in your own body is made of exactly the same atoms as that granite boulder. Carbon, oxygen, hydrogen, nitrogen, a scattering of others. There is no special living atom. There is no element that only appears in things that are alive. Take a person apart down to the level of individual atoms and lay those atoms in a pile, and there is nothing in that pile you could not also find in the dirt, in the air, in the sea, in a rock. The ingredients of you and the ingredients of the inert world are the same ingredients, and that means the difference between the living and the dead is not in the parts, it is in the arrangement. It is in what those ordinary, lifeless atoms are doing and how they are organized and the particular pattern they have fallen into. Which leads to the question that this whole video exists to ask. If life is just ordinary matter in a particular arrangement, then at some point that arrangement had to happen for the very first time. There had to be a first moment on this planet when atoms that had only ever behaved like a rock began, instead, to behave like life. Nothing was added. No new ingredient arrived. The same carbon and oxygen and hydrogen that had been drifting through the young Earth's oceans simply fell into a new pattern, and that pattern was alive. How did that happen? How does dead matter become living matter? And what exactly was the first living thing made of? That is where we are going tonight. We are going to walk all the way back, nearly 4 billion years, to a planet you would not recognize, and we are going to watch, as closely as the science will let us, the single most important event in the history of this world. The moment the boulder and the tree had not yet been separated. The moment matter, just once, did something it had never done before. Part 2. The first life had no ancestors. Before we can ask how life began, we have to be honest about one fact, and it is a fact that quietly removes every easy answer. The first living thing on Earth had no parent. It had no ancestor. There was nothing alive that came before it. We are so used to life coming from life that this is genuinely hard to hold in the mind. Every living thing you have ever encountered was produced by another living thing. You came from your parents. They came from theirs. A tree comes from a seed, which came from another tree. A bacterium comes from the division of a bacterium before it. Follow any living thing backward through time, and you find an unbroken chain of ancestors, each one alive, each one producing the next. This is so reliable, so universal, that for most of human history it was simply assumed to be the whole story. Life makes life. That is what life does. But trace that chain back far enough and you run into a hard edge, because the Earth itself had a beginning. Our planet formed roughly 4.5 billion years ago, condensing out of the disk of dust and gas surrounding the young sun. And the Earth of those first few 100 million years was not a place where anything could live. We call that span of time the Hadean Eon, and the name is not an accident. It is named for Hades. It was a world of magma, of a surface that in many places was molten rock, of an atmosphere of choking volcanic gases with no breathable oxygen at all. It was bombarded relentlessly by asteroids and comets, some of them large enough to boil the oceans away entirely and force them to condense again from the steam. Nothing alive could have survived that. Nothing alive did survive that, because there was nothing alive yet. So here is the situation we are actually facing. The chain of life, life producing, life, runs backward through nearly 4 billion years, and then it stops. It hits the Hadean Earth, a sterile, violent, lifeless world. And on the other side of that edge, there are no ancestors. There is no living thing. There is only chemistry. There is only rock and water and gas and energy. And yet, here you are. Here is the redwood and the bird and the bacterium and the entire overflowing abundance of life on this planet. So somewhere, in the gap between the lifeless Hadean world and the living world we know, something happened. Matter that was not alive became matter that was. The chain of life has a first link. And that first link was not forged by a parent, because it had none. It was forged by physics and chemistry alone. Now, I said that for most of human history, people simply assumed life makes life and left it there. That is not quite the whole truth, because there were always people who pushed on the question of the first life, and what they came up with is worth knowing, because their failures are how we learned what the real problem is. In the ancient Greek world, from roughly the 7th century before the Common Era onward, the great questions of where life came from became something close to a profession. Philosophers like Epicurus, like Lucretius, like Plato, turned these questions over for centuries, and the dominant answer they reached was the comfortable one. Life begets life. But the sharper thinkers among them knew that this only pushed the problem back, and so the question of that very first life remained, nagging, unsolved. In the 4th century before the Common Era, Aristotle gave the question its most influential answer, and it is an answer that would dominate human thought for nearly 2,000 years. Aristotle proposed what we now call spontaneous generation. He concluded that living things arise spontaneously from non-living matter as long as that matter contained what he called pneuma, a kind of vital heat. Worms, he reasoned, arose on their own from decaying manure. Insects sprang into being from the morning dew. Eels formed, newborn and complete, from nothing more than wet mud and rotting seaweed. It is easy, from where we stand now, to smile at this. But I want you to resist that, because Aristotle was not being foolish. He was being a scientist. He was looking at the world and constructing a theory to explain what he saw. And what he saw was real. Leave meat out and maggots appear in it as if from nowhere. Leave a damp corner alone, and small creatures show up in it that were not there before. To an observer without a microscope, without any knowledge of eggs too small to see, this genuinely looked like non-living matter generating life. Aristotle's theory was an honest attempt to explain a genuine observation. It was a theory of physics, in fact. It was the claim that matter, given the right conditions, organizes itself into life. And because it explained the observations, it lasted. It lasted through the entire Roman world, through the medieval period, into the dawn of modern science. The recipes even grew more elaborate. In the early 17th century, the Flemish physician Jan Baptist van Helmont, a serious and capable scientist for his time, wrote down a recipe for generating mice. Take a dirty shirt, he said, place it in a bin with some wheat, leave it for 21 days, and mice will be generated from it. He believed this. He had, he thought, seen it work. Over the following centuries, as observation grew sharper, the recipes for the larger animals collapsed one by one. People began to do the careful experiments. They covered the meat, and the maggots did not appear, because the flies could no longer reach it to lay their eggs. The mice, it turned out, had simply walked into the bin. For the visible animals, spontaneous generation died, but there was a holdout. There was one domain where spontaneous generation refused to die, and it was the domain that matters most for our story, the microscopic world. When the microscope revealed that a single drop of pond water or a flask of broth left standing teemed with countless tiny living things, the question came roaring back. Surely these, at least, the bacteria, the single-celled specks, surely these arose spontaneously from the broth itself. They appeared in any nutrient liquid left alone. Where else could they be coming from? It took until the 19th century and the French chemist Louis Pasteur to finally close the door. Pasteur designed an experiment of real elegance. He took flasks of nutrient broth and drew their necks out into long, curving, swan-like shapes. Air could still reach the broth freely through the open end, but the curve of the neck trapped dust and airborne particles, so that nothing solid, nothing carrying living spores, could drift down into the liquid. He boiled the broth to sterilize it, and then he waited, and the broth stayed clear. It stayed sterile, indefinitely, for as long as the neck remained intact. The moment he broke the neck and let dust fall in, the broth clouded with life within days. Pasteur had proven it. Matter, on its own, under ordinary conditions, does not make life. The tiny organisms in the broth had not been generated by the broth. They had drifted in from outside, from a living world that was already full of them. Spontaneous generation, after 2,000 years, was finally dead. Life, it seemed, only ever comes from life. And now you can feel the trap closing. Because Pasteur's result, as beautiful and correct as it is, leaves us with a paradox sharper than anything Aristotle ever faced. We know the Earth was once lifeless. We know that nothing alive carried over from before the planet existed. And we know, because we are here, that life now exists. So at some point, matter did make life. The thing Pasteur seemed to prove impossible is the thing that, undeniably, happened once. Somewhere in that gap of a few 100 million years on the early Earth, the most important event in this planet's history took place, and it was, in the most literal sense, the final act of spontaneous generation. The last time, and the only time it ever truly needed to happen, that the non-living made the living. So Pasteur did not really kill the question. He sharpened it into the form it still has today. He showed us that life does not arise from broth, in a flask, on a bench, in a week. He could not show, and did not show, that life never arises from the right chemistry, given the right energy, across the right span of time, on the scale of an entire young planet. The difference between his sterile flask and the early Earth is the difference between a teaspoon and an ocean, between an afternoon and 500 million years. Somewhere in that difference, the impossible became the inevitable. And to understand how, we first have to ask a question that sounds even simpler than it is. Before we can explain how life began, we have to know exactly what life is. Part 3. What life actually is. If you want to know how something began, you first have to know what that something is. And here we hit the first real surprise of the night, because life, the thing we are all so certain we can recognize, turns out to be remarkably difficult to define. Think about how you were probably taught to identify living things. Back in school, you were most likely given a list. Living things move, or grow, or take in energy, or respond to their surroundings, or reproduce. Tick enough boxes on the list, and the thing is alive. This is the definition by behavior, the definition by what a thing does, and it feels reasonable. But it falls apart almost the moment you press on it. Consider a fire. A fire moves. It grows, sometimes explosively. It consumes fuel and releases energy, which looks a great deal like a metabolism. It responds to its environment, flaring in a draft, dying when starved of air. It even reproduces, throwing off sparks that start new fires. By the behavior checklist, a fire is disturbingly close to alive, and yet no one believes a fire is alive. Hold that thought about fire. We are going to come back to it much later, and when we do, it is going to mean something very different than it does right now. Or consider a crystal, growing in its solution, building itself outward in a precise repeating pattern, taking in new material, even healing flaws in its own structure. Or consider a computer virus, a piece of code that copies itself, spreads, responds to its digital environment, and evolves as programmers and the virus's own variations push it. By a behavior-based definition, we would have to start calling some crystals and some software alive. The definition lets in far too much. It catches things we know in our bones are not living. So the behavior checklist fails. To find a definition that actually works, we have to do something that will become the central move of this entire video. We have to stop looking at what life does and start looking at what life is made of. We have to zoom in. We have to leave the scale of the organism, the redwood and the bird, and go down into the cell, and then further down still into the molecules. Because the real definition of life is not found in behavior, it is found in structure. So let us do that. Let us take the simplest, most stripped-down form of life that exists on Earth today, a single bacterium, and let us take it apart, gently, to see what is genuinely essential. We are looking for the irreducible core. We are looking for the parts you cannot remove without the thing no longer being alive. And when you do this, when you strip a living cell down to its absolute minimum, you find that two things remain, only two, and every living thing on this planet, without a single exception, has both of them. The first essential component is a self-replicating molecule. This is a molecule that carries, encoded within its own structure, the instructions for building another copy of itself. It is, in a sense, a message that contains the directions for writing the message again. In all life on Earth today, this molecule is DNA. The DNA inside your cells is a vast library of instructions, and crucially, it includes the instructions for copying the library. Without a self-replicating molecule, a thing cannot pass its structure forward in time. It cannot have descendants. It is a dead end. The second essential component is a self-contained metabolism. This is the machinery, the working part. A metabolism is a bounded set of chemical reactions that pulls in energy and raw materials from the surrounding environment and uses them to do the physical work of staying organized, of maintaining the structure, and of carrying out the copying. The self-replicating molecule is the blueprint. The metabolism is the construction crew and the power plant. The blueprint by itself just sits there. The metabolism is what reads it, acts on it, and keeps the whole enterprise running against the constant pressure of the universe to fall apart. A self-replicating molecule and a self-contained metabolism, instructions and machinery. That is the irreducible core of life. That is what the redwood has and the granite boulder does not. Not a special atom, not a vital spark, just two cooperating chemical systems working together inside a single bounded package. I want to let that settle, because it is a genuinely different way of seeing yourself than the one you carry around day to day. You feel like a unified being, a single self. But underneath that feeling, at the level where the question of life is actually decided, you are a population of, perhaps, 30 trillion cells, and each one of those cells is doing nothing more and nothing less than running these two systems. A molecule that holds the instructions to copy itself, and a chemical factory that does the copying and the living. The difference between you and the chair you are sitting in is not a soul, not a spark, not anything you cannot point to. It is the presence of these two systems. It is, in the end, chemistry, organized in a particular way. And this structural definition does something else valuable. It tells us exactly what we are looking for when we go hunting for the origin of life. We are not looking for the moment a spark of vitality entered dead matter. We are looking for something far more concrete. We are looking for the moment and the mechanism by which ordinary chemistry on the early Earth assembled these two specific things, a self-replicating molecule and a bounded metabolism, and got them working together. But before we go looking for that moment, this structural definition has one more gift to give us, and it is an unsettling one, because this definition has a grey zone. It has a case that does not cleanly fit, and that case is the virus. A virus is a strange object. At its core, a virus has a self-replicating molecule. It has the instructions, the genetic message, written in DNA or in its close relative RNA. So it has the first essential component of life. But a virus has no metabolism, none. It carries no machinery of its own. It has the blueprint, but no construction crew and no power plant. And so, on its own, a virus can do nothing at all. It cannot grow. It cannot copy itself. It is, by itself, as inert as a crystal. To reproduce, a virus must drift into contact with a genuine living cell, inject its instructions, and hijack that cell's metabolism, borrowing the machinery it does not own, forcing the cell's factory to build new viruses instead of new cell parts. So, is a virus alive? Ask that question of biologists, and you will not get a single answer. Some say yes, it has genes, it evolves, it is part of the living world. Some say no. It cannot do anything without a host. It fails the test. It is just a chemical package. The honest answer is that the question does not have a clean answer. A virus sits in the gap. It has one of the two systems and lacks the other. It is, you might say, halfway. And some scientists think that is not a coincidence. Some think the virus, or something like it, might be an actual relic, a surviving glimpse of a stage that life passed through on its way into being. A structure with the instructions, but not yet the machinery. A thing that is on the road to life, without having fully arrived. Hold on to that idea, because it is the first crack in the wall. We began tonight with the certainty that living and non-living are two separate kingdoms divided by an absolute boundary. And here, already, at the very first careful look, we have found something that does not sit on either side. We have found a halfway thing, and if there is a halfway thing, then the boundary was never a wall. It was always, at best, a slope, and the deeper we go from here, the steeper and the stranger that slope is going to become. Part 4. The ingredients were already there. We have our target. We are looking for the moment ordinary chemistry assembled two things, a self-replicating molecule and a metabolism. So the next question is the obvious one. What was that chemistry working with? What raw materials did the early Earth actually have lying around? And the first thing to understand is that not every kind of matter is suited to the job. The universe offers roughly 94 naturally occurring elements, and the overwhelming majority of them are simply wrong for building life. To see why, we have to think for a moment like a chemist, which means thinking about bonds. Every element has a personality, and that personality is defined by how it bonds. Some elements, the noble gases like helium and neon, are aloof. They barely react with anything at all. They will never build the long, intricate structures that life requires because they refuse to hold hands with their neighbours. Other elements bond, but badly for our purposes. Take silicon. Silicon is one of the most abundant elements in the Earth's crust. It is everywhere, in sand, in rock, in glass. And silicon can form bonds. But silicon's bonds are stiff and sluggish. They take large amounts of energy to make and to break, and they do not easily form the long, flexible, branching chains that biology depends on. Silicon is a building material for mountains. It is a poor building material for life. And then there is carbon. Carbon sits in a kind of chemical sweet spot, and it is no exaggeration to say that the entire phenomenon of life on Earth is a consequence of where carbon falls in the physics of bonding. Carbon is the fourth most abundant element in the solar system, so there is a great deal of it, and carbon bonds beautifully. It forms strong, stable bonds, but not bonds so strong they cannot be rearranged. It bonds readily with itself, linking into chains, rings, and branching trees of almost unlimited length and complexity. And it bonds just as readily with the other common light elements, with oxygen, with hydrogen, with nitrogen. Carbon is the element that can build structures intricate enough to encode information and run a metabolism, while still being flexible enough to be assembled and taken apart by the modest energies available in a warm ocean. Life is carbon-based, not by some cosmic preference, but because carbon is the one element whose bonding physics actually permits the job to be done. It is worth slowing down on that balance, because the precise nature of it is easy to skip past, and it is the quiet hinge that everything else swings on. Imagine an element whose bonds were too weak. The structures it built would fall apart almost as fast as they formed. Nothing could hold together long enough to do anything, to carry information, to run a sequence of reactions. There would be no stability, and so no continuity. Now imagine the opposite, an element whose bonds were too strong, like silicon. The structures it built would be rigid and permanent, yes, but permanent is not what life needs either. Life is not a statue. Life is constant change, constant building and unbuilding, molecules being assembled, used, taken apart, and recycled, all of it running on the modest energy budget available in water at the temperature of an ocean. An element whose bonds were too strong would lock its structures in place. They could not be edited, could not be copied, could not be metabolized. They would be chemically frozen. What life requires is the narrow middle ground, bonds strong enough to hold a structure together reliably, but weak enough that the structure can still be changed, copied, and dismantled using the gentle energies a planet's surface actually offers. Carbon sits, almost uncannily, in exactly that middle ground. It is stable enough to remember and flexible enough to change. And memory plus change, held together in the same substance, is very close to a definition of what life needs from its raw material. There is one more property of carbon worth naming because it explains the sheer variety of life's molecules. A carbon atom can form 4 bonds at once, reaching out in 4 directions. That number, 4, is generous. It means a single carbon atom can sit at a branch point, joining to several neighbors, so that carbon structures are not limited to simple straight chains. They can branch, fork, ring, and weave into 3-dimensional shapes of essentially unlimited intricacy. And shape, as we will see again and again tonight, is everything in the chemistry of life. The capacity to build complex, specific, 3-dimensional shapes is what allows a molecule to carry information and to act as a machine. Carbon's 4-way bonding is the structural freedom that makes that possible. So when we say life is carbon-based, we are not noting a trivial fact of chemistry. We are naming the deep physical reason that life on this planet was able to exist at all. So the early Earth had carbon, and it had the light elements carbon loves to bond with. The question is whether it had them in the right combinations, assembled into the actual building blocks that life needs. And the answer, remarkably, is yes. There are 3 families of building block that matter for our story, and there is good reason to think all 3 were present in some quantity on the young Earth. The first family is sugars. When you hear the word sugar, you probably think of something sweet, but to a chemist, a sugar is a particular class of small carbon, hydrogen, and oxygen molecule, and sugars do two essential jobs in life. They form part of the backbone of the genetic molecules, the scaffolding on which the instructions are hung, and they serve as fuel, the energy currency that a metabolism burns. Simple sugars form readily through known, ordinary chemical reactions. And here is something genuinely strange and wonderful. Related organic molecules, the chemical cousins of biological sugars, have been detected by astronomers out in the cold gas and dust of star-forming regions of our galaxy, the very clouds where new stars and planets condense. Some of the chemistry that life is built on does not even begin on a planet. It begins in interstellar space, before the planet exists. The second family is the nucleobases. These are small molecules built around nitrogen, and they are the heart of the matter, because the nucleobases are the letters of life's alphabet. In the genetic molecule, a sequence of just 4 different nucleobases, repeated in different orders, encodes every instruction a living thing possesses. The order of those 4 bases is the message. It is the molecular language in which the instructions for staying alive, growing, and reproducing are written. And these nitrogen-bearing molecules, too, can form through ordinary prebiotic chemistry, the kind of chemistry that needs no life to drive it. The third family is the amino acids. Amino acids are the building blocks of proteins, and proteins are the substance from which nearly all of a cell's working machinery is constructed. If the nucleobases are the letters of the instructions, the amino acids are the bricks the instructions tell you how to lay. Every enzyme, every molecular machine, every structural fiber inside a cell is, at bottom, a particular string of amino acids folded into a particular shape. So the picture forming is this. The early Earth, supplemented by chemistry delivered from space itself, was not a barren place chemically. It was, in a sense, a kind of vast organic kitchen, stocked with sugars and nucleobases and amino acids, the very building blocks that life is made of, all of them dissolved and drifting in the water of the young oceans. Scientists have a name for this. They call it the primordial soup, the prebiotic soup, a young ocean enriched with the molecular ingredients of life. I want you to sit inside that image for a moment, because it is one of the strangest and most beautiful facts in all of this. Picture yourself drifting in the warm, dark water of an ocean nearly 4 billion years old. The sky above is wrong, a sky no human could breathe, hazy and orange and lit by a sun that is younger and dimmer than the one you know. The moon hangs in that sky far larger and far closer than it does tonight, close enough to fill a frightening fraction of it. There is no sound of a living thing anywhere, because there are no living things. No fish move in the water around you. No bird crosses that alien sky. Nothing here is alive. Nothing here is even close to alive. And yet the water you are drifting in is not empty. It is thick, invisibly, with the ingredients, sugars that may have formed in a cloud of interstellar dust before the sun ignited, nitrogen compounds that will one day be the letters of a genetic code, amino acids that will one day fold into the machinery of a cell. They are all here, all around you, suspended in the dark water, drifting, colliding, drifting apart again. The kitchen is fully stocked. Every ingredient that life requires is present in this ocean. And still, there is no life. Because having the ingredients, as we are about to see, is not remotely the same thing as having a meal. The building blocks alone are not life. A pile of bricks is not a house. The question that now opens in front of us, the question that takes up the rest of this journey, is how those scattered, drifting building blocks came together, in the right way, in the right order, to build the two systems that define a living thing. And the first step toward answering that is to ask whether the building blocks themselves can really form from nothing but dead chemistry and raw energy. That is not a question we have to guess at. Because in 1953, 2 scientists put it to the test. in an experiment that became one of the most famous in the history of science. Part 5. A Spark in a Jar. In 1953, at the University of Chicago, a graduate student named Stanley Miller, working under the chemist Harold Urey, decided to stop speculating about the primordial soup and simply try to make some. The idea behind the experiment was elegant in its directness. If the early Earth really did have the right ingredients and the right energy to produce life's building blocks, then you should be able to recreate those conditions in glassware, on a bench, and watch it happen. So Miller built an apparatus, a closed loop of glass flasks and tubes. Into it he sealed what was then believed to be the recipe of the early atmosphere. He used water to stand in for the ocean. And above the water, he placed a mixture of gases, methane, ammonia, and hydrogen, the gases scientists of that era thought had filled the Hadean sky. Then he needed energy, because chemistry does not happen without a push. On the early Earth, that push would have come from many sources, but one of the most dramatic is lightning. Picture the storms over that young world, the thunderclouds piled over the first volcanic mountains, and the lightning spearing down out of them into the sea. So Miller put electrodes into his apparatus and sent a continuous electric spark through the mixture of gases, his own small caged lightning. And then he let it run. He let the water boil and circulate as vapor, let it mix with the gases, let the spark crack through it again and again, let the products cool and rain back down into the pool of water, around and around the loop. Within days, the water changed. It began to darken, to turn a deep reddish brown. Something was being made in there, and when Miller analyzed what that something was, he found that his cage storm had produced organic molecules that had not been there when he started. And not just any organic molecules. He found amino acids, the building blocks of proteins. The bricks of life's machinery had assembled themselves inside a sealed jar, out of nothing but water, a few simple gases, and electricity. I want to be precise about what this did and did not prove, because the Miller-Urey experiment is often misunderstood in both directions. It did not create life. It did not come anywhere close to creating life. What it did was settle one specific, crucial question. Before 1953, you could still reasonably wonder whether the building blocks of life required life to make them, whether amino acids were, in some sense, special, products that only a living process could produce. Miller-Urey closed that question. It showed, concretely and undeniably, that the building blocks of life are not special. They are ordinary chemistry. Given the right simple ingredients and a source of raw energy, life's bricks assemble themselves, with no life involved at all, in a matter of days. Let yourself stand inside that apparatus for a moment, shrunk down small. Below you, the pool of dark water. Above you, the still mixture of gases waiting. And then the spark. A thread of lightning cracks through the vapor, blinding and brief, and the air shudders with its energy. And in the wake of that spark, in the settling quiet afterward, something new exists that did not exist a heartbeat before. Molecules have rearranged. Atoms that were drifting as simple gas have been driven together into a more complex form, a form with structure, a form that is one of the building blocks of every living thing that will ever exist on this planet. You are watching the universe, calmly and without ceremony, demonstrate that the gap between plain chemistry and the stuff of biology is far narrower than it appears. No life is needed to make the bricks of life. Energy and matter will do it on their own. Now, the story of this experiment did not end in the 1950s, and the two ways it has continued are both worth knowing, because together they show you how real science works. The first development came after Stanley Miller died in 2007. Miller, it turned out, had been a careful man. He had never thrown away the sealed vials from his original experiments. They had sat in storage for half a century, and after his death, his former student Geoffrey Bader took those preserved vials and analyzed them again, this time with modern instruments far more sensitive than anything Miller had access to in 1953. And the modern analysis found something striking. Miller's original experiment had worked far better than Miller himself ever knew. Where he had been able to identify only a handful of amino acids, around 5, the modern reanalysis in 2008 identified 23 different amino acids in those old samples. The experiment had been quietly more successful for 50 years than its own creator realized. The primordial soup was richer than he could see. The second development is more challenging, and it is the one that shows real intellectual honesty. Since Miller's day, planetary scientists have learned a great deal more about the early Earth, and they now believe that the early atmosphere was probably not the strongly reactive mixture of methane and ammonia that Miller used. It was more likely a more neutral mixture, dominated by carbon dioxide and nitrogen. And here is the difficulty. If you run the Miller-Urey experiment with that more neutral, more realistic atmosphere, it does not work nearly as well. The amino acids do not pour out the way they did with Miller's original recipe. Now, you might think that this quietly demolishes the whole experiment. It does not, and understanding why is important. The discovery does not refute Miller-Urey. It relocates it. The strongly reactive conditions Miller used were not wrong. They were simply not the conditions of the whole planet's atmosphere all at once. They were the conditions of particular places and particular moments. After a large asteroid slammed into the early Earth, the impact would have filled the local sky, for a time, with exactly the kind of hydrogen-rich, reactive plume that Miller-Urey thrives on. Around volcanic vents, in specific pockets, the chemistry would have been similar. The point is that the early Earth was not chemically uniform. It was a patchwork. And in the right patches, at the right times, the Miller-Urey reaction would have run beautifully. The chemistry is entirely real. The question simply shifted from whether life's building blocks form on their own, which is settled, to where, exactly, on that varied young planet, they formed most abundantly. So this is where the experiment leaves us, and it is a strange place. We now know, with confidence, that the building blocks of life build themselves. The bricks are not the mystery. Sugars, nuclear bases, amino acids, all of them will assemble from dead chemistry given energy and time, and the early Earth had energy and time in abundance. The primordial soup was real, and it was stocked. And yet, here is the thing that should be nagging at you. If it is this easy, if the building blocks just fall out of a jar with a spark in it, then why, after 70 years of trying, has no laboratory on Earth ever managed to take that soup and get life out of it? Why is the origin of life still, genuinely, a mystery? Because the building blocks are not the hard part. The hard part is everything that comes after the building blocks. The hard part is assembly. And waiting for us at the very center of that assembly problem is a paradox so perfectly circular that for a long time it looked less like a scientific puzzle and more like a closed door. Part 6. The loop that cannot start. Here is the paradox. And I want to build it carefully, brick by brick, because it is the single hardest knot in the entire origin of life. And for a long time, it looked like a knot with no end to pull. Remember the two essential components of life: a self-replicating molecule, which holds the instructions, and a metabolism, the machinery that does the work. In all life on Earth today, the self-replicating molecule is DNA, and the machinery is built mainly out of proteins. So let us look closely at how those two actually relate to each other inside a living cell, because the relationship is where the trouble lives. DNA holds the instructions, but DNA, on its own, is almost completely helpless. It is a magnificent library, but it is a library with no librarian and no readers. The DNA molecule cannot copy itself. It cannot read itself. It cannot do anything with the information it holds. To be copied, to be read, to be acted upon, DNA needs machinery. It needs proteins. There are specific proteins whose entire job is to grip the DNA, unzip it, and copy it. There are other proteins whose job is to read the instructions and carry them out. Without proteins, DNA is an inert thread. It just sits there, a message no one can open. So DNA needs proteins. Fine. Then let us look at the proteins. Where do proteins come from? A protein is a string of amino acids folded into a precise shape, and the precise order of those amino acids is what makes the protein work. So where is the order specified? Where are the instructions for building each protein kept? They are kept in the DNA. The DNA is the blueprint for every single protein the cell makes. You cannot build a protein without reading its instructions out of the DNA. Now hold both of those facts in your mind at the same time, because together they form a perfect closed circle. DNA cannot be copied or used without proteins, and proteins cannot be built without the instructions held in DNA. DNA needs proteins. Proteins need DNA. Each one requires the other to already exist. This is the chicken and the egg, made molecular and made absolute. And I want to be clear that this is not a loose analogy or a figure of speech. It is a precise structural fact about how life works. Picture trying to start this system from scratch on the early Earth. Suppose, by some chemical luck, you assemble a strand of DNA first. It sits there, useless, inert, because there are no proteins to read it or copy it. It cannot do anything. It cannot make descendants. It is a dead end, and eventually it drifts apart. Now suppose instead you assemble some proteins first. They might be capable little machines, but they have no instructions, no blueprint, no way to be copied or specified or passed on. When they break down, as all molecules eventually do, there is nothing to rebuild them. They too are a dead end. You cannot start with DNA, because DNA without proteins is helpless. You cannot start with proteins, because proteins without DNA cannot be reproduced. And you cannot start with both at once, because the odds of both of these wildly complex, mutually matched systems assembling simultaneously, by chance, in the same tiny pocket of ocean, are so vanishingly small that no scientist takes the idea seriously. For a long time, this was where the conversation about the origin of life simply stalled. The loop seemed unbreakable. We are right back, in a sense, at the oldest answer of all, the answer of the ancient Greeks. Life begets life. The instructions need the machinery needs the instructions, and there is no way in. The chicken needs the egg needs the chicken, and the door appears to be closed. And I want to dwell on just how severe this problem looked, because it is easy, once you know the answer, to underestimate how genuinely frightening this paradox was to the scientists who first stared at it. It is not a problem of probability. Probability problems can be solved by time and by scale. If something is merely very unlikely, then a large enough planet and a long enough stretch of millions of years can make it happen anyway, because unlikely things do occur if you roll the dice often enough. But the chicken and egg paradox is not a probability problem. It is a problem of logical structure. It does not say that life is unlikely to start. It says, on its face, that life cannot start, that the system has no possible first state, that there is no configuration you could place on the early Earth that would begin the process. A locked door can be opened if you find the key, but this looked less like a locked door and more like a door painted onto a solid wall, a door that was never a door at all. Consider the depth of the trap from one more angle. Suppose you are extraordinarily lucky. Suppose, by some staggering chemical accident, the early ocean assembles not just a strand of DNA and not just a few proteins, but a strand of DNA and the exact matching set of proteins it needs all at once, in the same small pocket of water, at the same moment. Even then, even with that absurd stroke of luck, the system would still fail. Because those proteins would do their work and break down, as all molecules eventually do, and the cell would need to build fresh ones. And to build fresh ones, it would need to read the DNA. And to read the DNA, it would need a whole further set of proteins, which would themselves break down, and so on, forever. The dependency does not just block the first step, it blocks every step. A system where each part is perishable and each part can only be replaced by the other part is a system that cannot sustain itself, even if you hand it a perfect starting configuration for free. That is how complete the trap appeared. It was not a gap to be bridged. It was, apparently, a contradiction. But notice the hidden assumption inside the paradox. The whole circle depends on the idea that life must be built from these two specific kinds of molecule. Instructions made of DNA, machinery made of protein, two separate substances, each specialized for one job, each helpless without the other. That division of labor is real in every living thing today. But what if it was not always so? What if, at the very beginning, life did not use two molecules at all? What if there was once a single molecule that could do both jobs? A molecule that could carry instructions, like DNA, and also act as machinery, like a protein. If such a molecule existed, the entire paradox would dissolve. There would be no chicken and no egg. There would be just one thing, copying itself, with no partner required. The loop would never need to be entered, because the loop would never have formed in the first place. For decades, this was only a hope, a logical necessity with no candidate to fill it. The molecule that could break the paradox would have to be a genuine double agent, equally at home as a message and as a machine. And then scientists realized that such a molecule was not hypothetical at all. It already exists. It is inside every cell of your body right now, doing quiet, essential work. We had been looking at it the whole time, and we had badly underestimated what it could do. Its name is RNA. Part 7. The molecule that is both. To understand why RNA breaks the paradox, you have to understand what RNA is, and you have to set aside the supporting role it is usually given. If you learned any biology, you probably learned about RNA as DNA's assistant, the messenger. In a modern cell, that is largely what RNA does. DNA holds the master instructions safe in the cell's core, and when a particular instruction is needed, a temporary copy of it is made in RNA, and that RNA copy carries the message out to where the proteins are built. RNA, in this telling, is the errand runner, the middle manager, useful but not the star. That description is true, and it is also a profound underestimation, because RNA is capable of far more than running errands. Structurally, RNA is a close cousin of DNA, but a simpler one. DNA is the famous double helix, two strands wound together. RNA is typically a single strand, and that single strand, like DNA, is built from a sequence of nucleobases, those letters of the genetic alphabet. So RNA can do the first job. A strand of RNA, with its sequence of bases, can carry information. It can be a set of instructions, and it can serve as a template to be copied. That much it shares with DNA. But RNA can do something DNA essentially cannot, and this is the key to everything. Because RNA is a single strand, it is floppy, it is flexible, and a long, floppy single strand of RNA does not just lie there straight, it folds. It coils back on itself, twisting and bending until it settles into a complex, three-dimensional shape. And here is the thing about three-dimensional molecular shapes. Shape is what machinery is made of. The reason a protein can do work, can grab a molecule, can speed up a chemical reaction, is that it folds into a precise shape with precisely placed working surfaces. And RNA, when it folds, can do the very same thing. A folded strand of RNA can act as a machine. It can be a catalyst. It can grip other molecules and drive chemical reactions, the exact job we thought only proteins could do. An RNA molecule that acts as machinery, as a catalyst, has a name. It is called a ribozyme, and ribozymes are not a hypothesis. They are not something scientists wish existed. They are real. They exist in your cells right now, and one of them is doing one of the most important jobs in all of biology. At the very center of the ribosome, the great molecular machine that builds every protein in your body, the part that actually performs the core chemical reaction, the part that does the essential work, is not a protein at all. It is RNA. It is a ribozyme. The machine that builds the machinery has a piece of RNA at its beating heart. Life left us a clue, hidden in plain sight, about what came first. So look at what RNA can do. It can carry information, like DNA, and it can act as a machine, like a protein. It is the double agent. It is the single molecule that does both jobs. And that means RNA is exactly the thing the paradox required. It is the way in, it is the answer to the chicken and the egg. The hypothesis built on this realization is called the RNA world, and it is the most influential idea in the entire study of life's origins. The idea was first suggested in the early 1960s by Alexander Rich, and it was given its memorable name, the RNA world, by Walter Gilbert in 1986. And what it proposes is this. The first life did not use DNA. It did not use proteins. The first life ran entirely on RNA. RNA was both the instructions and the machinery. There was no chicken and no egg, because there was only one thing, a molecule that was its own message and its own reader, copying itself, with no partner needed. Let me show you how this could actually unfold, down in the primordial soup, with no life present at all, with nothing but chemistry and physics doing the work. Start with the soup we have already stocked. The young ocean, thick with drifting building blocks. Among those building blocks are sugars and nuclear bases, the very pieces from which RNA is made. In the ordinary churn of the water, by simple chemistry, those pieces sometimes join. A base links to a sugar, links to another base, and a short strand of RNA exists, briefly, where a moment before there were only loose parts. Most of these strands are nothing. They form, and they fall apart again. The soup is making and unmaking short scraps of RNA constantly, pointlessly, like foam on a wave. But not every strand is equal. Some strands, purely by the accident of which bases happen to be in which order, are more stable than others. They hold together longer before the water tears them apart. And some strands, again purely by accident of sequence, fold into shapes, and a few of those folded shapes are not just stable, but useful. A few of them, by sheer chance, fold into a shape that can grip another strand of RNA and help it copy. A molecular machine, assembled by accident, whose function is to make more RNA. And the moment you have even one strand that is good at copying RNA, everything changes, because now you have the beginning of a process, and the process is selection. The strands that are more stable last longer. The strands that copy more reliably make more descendants. Strands that are fragile or that copy poorly fade out. Strands that are tough and that copy well come to fill the soup. No life is making this happen. No mind is choosing. It is pure physics. It is simply the fact that things which persist and copy will, over time, outnumber things which fall apart and do not. An ecosystem of competing RNA molecules emerges in the primordial water, diversifying, some strands getting better at the copying game, the whole population slowly improving, generation after generation, with not a single cell, not a single protein, and not a single strand of DNA anywhere in sight. This is not just a nice story. The laboratory has been steadily pushing it from speculation toward demonstration. One of the central challenges has always been whether an RNA molecule could really copy other RNA molecules well enough to sustain this. And in recent years, researchers have engineered RNA enzymes that can do exactly that, accurately copying other functional RNA strands and copying them in a way that still allows new variants to arise. That last part matters enormously. A copier that makes perfect copies and nothing else can only ever produce more of the same. But a copier that makes mostly accurate copies, with occasional small variations, is something far more powerful. It is the minimum engine of open-ended evolution. It can change, it can improve, it can explore. So pause here and feel where we have arrived, because we have just walked through a door in a wall that looked, a few minutes ago, completely solid. The chicken and the egg paradox, the closed loop that stalled this entire field for years, has a solution, and the solution is a molecule that exists inside you right now. RNA, the double agent, message and machine at once, dissolves the paradox by making it unnecessary. The loop never had to be entered, because before there were two molecules, there was one. And yet, this RNA world, this ecosystem of self-copying molecules, drifting and competing in the open sea, is still not life. It is closer than anything we have seen. It has the self-replicating molecule, the first of life's two essential components, in a primitive form. But it is missing the second component, and it is missing something else, something more basic, that the second component requires. And to see what that is, we have to confront a problem that has nothing to do with information or paradox, and everything to do with the simple, brutal physics of trying to do delicate chemistry in a very, very large ocean. Part 8. The box that physics built. Here is the problem with the RNA world as we have so far described it. It is too exposed. It is too thin. It is spread across an entire ocean, and an ocean, for the delicate business of becoming alive, is a terrible place to work. Think about what a metabolism actually requires. A metabolism is a set of chemical reactions that have to happen in concert, the product of one reaction becoming the raw material for the next, a whole linked sequence running together. And for a chemical reaction to happen at all, the molecules involved have to physically find each other. They have to collide. The more concentrated they are, the more crowded together, the more often they collide, and the faster the chemistry runs. Dilute them, spread them thin, and the collisions become rare, and the chemistry slows to nothing. Now picture our RNA strands and our scattered building blocks dissolved in the early ocean. The ocean is vast, almost beyond comprehension at the scale of a molecule. A single strand of RNA drifting in that water is effectively alone. The other molecules it would need to react with, to build anything, to sustain anything, are so far away, so hopelessly diluted through that enormous volume, that the odds of the right pieces meeting are essentially zero. And even when something useful does form, the open ocean immediately works against it. Whatever a strand builds up drifts away. Whatever concentration gathers is instantly dispersed, and stray molecules drifting in from everywhere constantly interfere, disrupting the delicate reactions, breaking down the fragile products. Even a small pond, even a puddle, is, from the point of view of a single molecule trying to start a metabolism, an impossibly large and hostile space. The chemistry of life cannot get organized while it is smeared across an ocean. It is like trying to build a fire while standing in a high wind, in the dark, with the fuel scattered across a field. The energy and the materials might all be present, but they are too far apart, and the environment is too disruptive for anything to catch. What the chemistry of life needs, desperately, before it can become a metabolism, is a box. It needs a container. It needs a small, enclosed space where the right molecules are held together, concentrated, crowded, protected from the disruptive, wider world. It needs an inside, a place separate from the ocean where the concentration can build and the reactions can run and the products cannot simply drift away. And here is one of the most beautiful facts in this entire story. The early Earth did not have to invent that box. The box builds itself. The box is a direct, automatic, unavoidable consequence of physics. And the physics that builds it is the physics of a particular kind of molecule called a fatty acid. Fatty acids, and their close molecular relatives, are simple molecules, and like the other building blocks we have met, they form readily in prebiotic chemistry. They would have been present in the soup. But fatty acids have a special property, a kind of split personality, and that property is everything. A fatty acid molecule has two ends, and the two ends feel completely opposite ways about water. One end of the molecule is attracted to water. It wants to be surrounded by water, immersed in it, in contact with it. We call that end hydrophilic, water-loving. The other end of the very same molecule is repelled by water. It cannot stand to be in contact with water and will do anything to escape it. We call that end hydrophobic, water-fearing. So a single fatty acid molecule, dropped into water, is in an impossible situation. It is one molecule with two ends that want two contradictory things. The water-loving end wants in, the water-fearing end wants out. The molecule cannot tear itself in half to satisfy both. It is trapped in a physical contradiction. So what happens when you have not one but countless fatty acid molecules, all of them in water, all of them facing this same impossible bind? They solve it. Not by any plan, not by any guidance, not by any machinery. They solve it the way physics always solves things, by falling, automatically, into the arrangement that resolves the tension, the lowest energy state available to them. And the arrangement that resolves the tension is exquisite. The fatty acid molecules gather together, and they line up, and they form a sheet, a film 2 layers thick. In that double layer, all the water-fearing ends turn inward, toward each other, huddled together in the middle of the sheet, hidden from the water, shielded. And all the water-loving ends turn outward, on both faces of the sheet, facing the water, bathed in it, content. Every end of every molecule gets what it wants. The contradiction is resolved. But a flat sheet has edges, and at the edges, the water-fearing interior is still exposed. So the sheet does the last thing physics requires. It closes. It curls around and seals into a sphere. A tiny, hollow, spherical shell, 2 molecules thick, with a protected interior and an exterior, both faces in comfortable contact with water, and no exposed edges anywhere. This self-assembled spherical shell is called a vesicle, and it is, without exaggeration, the first room in the universe with an inside. I want you to watch this happen, slowly, at the scale where it happens. Come down to the size of a single fatty acid molecule, drifting in the warm prebiotic water. Feel the contradiction of it, the one end straining toward the water, the other recoiling from it, an object at war with itself. And now feel what happens as other molecules like it drift near. The water-fearing ends find each other, almost with relief, and cling. More arrive, and more. And a sheet begins to build, the fearful ends turning inward into a shared shelter, the loving ends turning outward into the water. And then feel the sheet begin to curve, the edges reaching around, until with a kind of silent closing the sphere completes itself, and there is, suddenly, an inside. A pocket of water, enclosed, separated, held apart from the entire rest of the ocean by a wall that built itself. No instruction was given, no machine did this, no information was required. The structure assembled because, given water and these molecules, it is simply what the physics does. It could not happen. And this is not speculation either. In the laboratory, much of this work done by the group of the scientist Jack Szostak, fatty acid vesicles, have been studied in enormous detail, and they turn out to be far more lifelike than a passive bubble has any right to be. These vesicles can grow, taking in more fatty acid molecules and enlarging. They can divide, splitting into two smaller vesicles when disturbed. They can let useful small molecules pass inward across their membrane, nutrients drifting in from outside. And the process can even be self-promoting, with existing vesicles speeding the formation of new ones. They grow, they divide, they feed. They are doing a faint, primitive sketch of the things we associate with life, and they are doing it as plain chemistry, with no genes and no metabolism, simply because that is how these molecules behave in water. Now bring the two halves of the story together. Out in the soup, we have the RNA world, an ecosystem of self-copying molecules, the instructions, the first essential component. And also in the soup, forming constantly and automatically, we have these vesicles, these self-assembled boxes with a protected inside. And inevitably, in all that vast churning of the early ocean, the two things meet. A vesicle forms, or grows, around a stretch of water that happens to contain strands of RNA. And now the RNA is inside. It is enclosed. It is held in a small, concentrated, protected space, sheltered from the disruptive ocean, its building blocks no longer hopelessly diluted, but crowded together within a wall. This object has a name. It is called a protocell. And the protocell is the most important structure in this entire story, because for the very first time, both of life's essential components exist together, in one place, in one bounded package. There is a self-replicating molecule, the RNA, on the inside, and there is a container, a membrane, defining an inside and an outside, concentrating chemistry, allowing a primitive metabolism to begin to run. Instructions and a box for the machinery. The two requirements of life, finally, in the same place at the same time. I am not going to tell you the protocell is alive. It is not, or at least not yet, not clearly. But look at how far the matter in front of us has come. We began with scattered atoms, the same atoms as a rock. We watched them form building blocks on their own. We watched the building blocks form self-copying RNA on their own. We watched fatty acids form a protective box on their own. And now we have the box with the self-copying molecule inside it. The whole assembly built with nothing but ordinary chemistry and the relentless tendency of physics to fall into the arrangements it prefers. Not one step of this required a designer, a spark, or a plan. Every step required only matter, energy, water, and time. And that should make us ask a much deeper question. Not how anymore, but why? Why does matter do this? Why does it climb, step after step, toward arrangements that look more and more like life? Is it fighting some uphill battle against the nature of the universe? Or is it possible that this climb is not a struggle at all, that the universe is not resisting the emergence of life, but, in some deep and surprising way, encouraging it? Part 9. Life runs the universe's errand. There is an objection to everything I have just told you, and it is a serious one, and if you have a certain kind of mind, it may already have occurred to you. The objection comes from one of the deepest and most reliable laws in all of physics, the second law of thermodynamics. And on the surface, the second law of thermodynamics seems to say that the entire story of this video is impossible. Let me put the second law in plain terms. It says that in any isolated system, disorder always increases. Things fall apart. Order decays into chaos. A sandcastle, left alone, becomes a smooth, featureless mound, and then a flat beach. A hot cup of coffee, left alone, cools to room temperature and never spontaneously heats back up. A building, left alone, crumbles. The universe, taken as a whole, is running relentlessly in one direction, from order toward disorder. Physicists measure disorder with a quantity called entropy, and the second law, in its starkest form, says that the total entropy of the universe is always increasing. Disorder always wins, in the end. Now look at life against that backdrop. A living thing is one of the most exquisitely ordered arrangements of matter in the known universe. A single cell contains billions of molecules, each of a specific type, each in a specific place, doing a specific job, the whole thing organized to a degree that makes the finest human machine look crude. And life does not just maintain that order, it builds it, again and again, taking the scattered, disordered molecules of food and air and assembling them into the staggering order of a new organism. So here is the objection, sharp and clear. The universe runs toward disorder. Life runs toward order. Life appears to be a direct violation of the second law of thermodynamics. It appears to be matter doing the one thing physics says matter cannot do, spontaneously becoming more ordered, climbing uphill against the deepest current in nature. And if that were true, then the origin of life would not just be a mystery, it would be an impossibility, and every step I have described to you tonight would be a step that physics forbids. But life does not violate the second law, and understanding exactly why is the single most important idea in this entire video, because it does not just rescue the story, it turns the story completely upside down. The resolution hides in 3 small words in the statement of the law. The second law says that disorder always increases in an isolated system. An isolated system. A system sealed off, exchanging nothing with its surroundings, no energy in, no energy out, no matter in, no matter out. In a truly isolated system, yes, order decays and entropy rises without exception. But here is the thing. A living thing is not an isolated system. It is the opposite of an isolated system. A living thing is an open system, and it is open in the most dramatic way imaginable. It is a system with energy and matter constantly flowing through it. You take in food, which is chemical energy. You take in oxygen. You give off heat, you give off waste. A plant takes in sunlight, a flood of energy from outside. Life is not a sealed box. Life is a channel, a place through which energy pours. And once you see that, the apparent violation dissolves, and something much stranger takes its place. A living thing maintains its internal order, yes, but it does not do so for free, and it does not do so in isolation. It maintains its own order by reaching out into its surroundings and creating disorder there. It takes in concentrated, high-quality energy, food, sunlight, and it dumps out degraded, low-quality energy, waste heat, scattered molecules. Every moment you are alive, you are exporting disorder into the world around you. Your body radiates heat, warming the air, increasing its entropy. The order inside you is paid for, in full, by a larger quantity of disorder created outside you. And when you do the complete accounting, when you add up the small decrease in entropy inside the living thing and the larger increase in entropy it creates in its surroundings, the total always rises. The second law is not violated. It is not even bent. It is obeyed perfectly every single time. Life maintains its island of order by generating an even greater ocean of disorder around it. Life does not defeat the second law of thermodynamics. Life is one of the universe's most effective ways of carrying the second law out. Sit with that, because we have just turned the objection inside out. We started with the worry that life is a rebellion against the universe's deepest law, and we have ended somewhere else entirely. Life is not a rebellion against that law. Life is an instrument of it. Life is something the second law is happy to permit, because life is very, very good at the law's central business, which is the production of entropy. And once you have seen that, you can take one more step, and it is the step that changes how you see your own existence. Because if life is a good way of producing entropy, of dissipating energy, of moving the universe toward disorder, then we have to ask a new question. We have always assumed that order is hard, that order is rare, that order is the thing the universe resists. But what if, under the right conditions, order is exactly what the universe produces? Think about where you find strong flows of energy in nature. Think about a pot of water, heated steadily from below. At first, the water just sits there, but push enough energy through it, and something remarkable happens. The water spontaneously organizes itself. It forms neat, rolling cells of circulation, an ordered pattern of churning hexagons, structure appearing out of nothing but a flow of heat. Think of a hurricane, a vast, intricately organized structure, a coherent engine hundreds of miles across, that assembles itself spontaneously wherever there is a strong enough flow of heat from a warm ocean into a cool atmosphere. The structure forms because it is good at moving the energy. It is, in a real sense, a tool the system builds to dissipate the energy gradient faster. There is a line of thinking in modern physics, developed in recent years by the physicist Jeremy England, among others, that takes this idea and points it straight at the origin of life. The proposal is sometimes called dissipation-driven adaptation, and the core idea is this. When you have a flow of energy passing through a group of molecules, and those molecules are of a kind that can be rearranged, then the arrangements that are best at absorbing and dissipating that energy will tend to be the ones that persist and get reinforced. Matter, in a strong and steady flow of energy, will tend to restructure itself into forms that are better and better at dissipating that energy. And a structure that is extraordinarily good at capturing energy and using it and degrading it and dumping the disorder outward, a structure like that has another name. We call it life. In this view, life is not a fluke. Life is not a one-in-a-cosmos accident that barely happened. Life is something matter tends toward, the way water tends downhill, whenever it finds itself in a sufficiently strong flow of energy with the right materials to work with. The young Earth was drenched in energy flows, sunlight pouring down, heat welling up from the planet's interior, chemical energy stored in the restless reactions of rock and water and air. And in that flood of energy, matter did what this view says matter does. It climbed, it organized, it built structures that were better and better at riding the energy flow. And one of those structures, eventually, was alive. I want to name plainly the realization at the center of this, because it is the emotional core of the whole video, and it inverts the story most people carry about themselves. The common picture of life is that it is precious and fragile precisely because it is improbable, a tiny, defiant flame of order flickering against the cold, vast, hostile darkness of a universe that wants nothing more than to snuff it out. It is a moving picture, but it may simply be wrong. The thermodynamics suggests the opposite. The universe is not hostile to life. The same relentless drive toward disorder that crumbles the sandcastle and cools the coffee is the very drive that, in the right setting, builds the most ordered things that exist. You are not a rebel against the second law of thermodynamics. You are one of its finest achievements. You are not an exception the universe grudgingly tolerates. You may be precisely the kind of thing the universe, given energy and matter and time, reliably produces. The drive toward disorder and the existence of you are not enemies. They are, astonishingly, the same thing. And if that is true, then the question of where life began becomes much more concrete. We should look, on the early Earth, for the place where the energy flow was strongest and steadiest. We should look for the spot where the universe's engine was running hardest, because that, the thermodynamics says, is where matter would have climbed the highest. That is where we should expect to find the cradle. Part 10. The cradle was already warm. So where was it? Where on the young Earth did the matter make its final climb? If life is matter, organizing itself in a strong flow of energy, then we are looking for a specific place, a specific setting, where the conditions were right. And the science offers two leading candidates. They are very different places, and they represent two different ideas about what kind of energy flow did the work. The first candidate is the gentle one, and it is the oldest. It goes all the way back to Charles Darwin himself, who in 1871, in a private letter, allowed himself to speculate. He imagined that life might have begun in what he called a warm little pond, a small, shallow, sunlit pool of water, rich with the right chemicals, where the building blocks could gather and combine. For a long time, this was just a lovely phrase. But the modern version of the warm little pond idea is a serious scientific proposal, and it has a clever engine at its heart. The engine is the cycle of wetting and drying. Picture a shallow pool at the edge of a volcanic landscape, fed by rain or by a hot spring, and exposed to the sun and the heat. That pool does not simply sit there. It dries out, partly or fully, and then it refills, and it dries again, over and over, a rhythm of wet and dry. And those drying steps are doing real and important chemical work. Remember the dilution problem, the difficulty of getting molecules concentrated enough to react. When a pool dries, the water leaves, but the dissolved building blocks do not. They are left behind, crowded closer and closer together as the water retreats, forced into contact. And more than that, the act of drying, of removing water, actually drives a particular kind of chemical reaction, the kind that links small molecules into long chains. Joining building blocks into chains is difficult to do while they are floating in bulk water. But as a pool dries, the dehydration itself pushes that joining reaction forward. So a pool that wets and dries, again and again, becomes a natural engine for building the long molecules life needs, concentrating the ingredients on every dry phase, then redissolving and remixing them on every wet phase. Cycle after cycle, the chains get built. It is patient, and it is gentle, and it is powered ultimately by the sun and the rhythm of the young Earth's days. The second candidate could hardly be more different. It is not sunlit and shallow. It is in total darkness, under crushing pressure, at the bottom of the sea. It is the deep-sea hydrothermal vent. Hydrothermal vents are places on the ocean floor where water, seeping down into the hot rock of the young crust, is heated and driven back up, emerging as warm or hot mineral-rich fluid. And the kind of vent that interests origin of life scientists most is a particular type called an alkaline hydrothermal vent. These are not the violent black smokers you may picture. They are gentler, cooler, and they build, over time, towering porous structures of mineral, honeycombed through with countless tiny chambers and channels. And the alkaline vent has, built into it, for free, two of the exact things our story has been searching for. The first is compartments. Remember how badly the chemistry of life needed a box, a small enclosed space to concentrate its reactions. The fatty acid vesicle was one answer, but the alkaline vent offers another, made of stone. The vent structure is riddled with microscopic mineral pores, tiny interconnected chambers, each one a natural reaction vessel, each one a small enclosed space where molecules can gather and concentrate and react, sheltered, while the warm fluid seeps through. The vent comes pre-built with billions of little boxes. But the second thing the vent offers is the deeper one, and it goes straight back to the thermodynamics we just discussed. The second thing the vent offers is a natural, sustained flow of energy, of exactly the kind life uses. As the vent fluid, which is alkaline, meets the surrounding early ocean, which was mildly acidic a difference is set up across those thin mineral walls. On one side, one chemistry, on the other side, another. And a difference like that, a gradient maintained across a barrier, is stored energy. It is a battery. And here is the part that should genuinely stop you. The specific kind of gradient an alkaline vent maintains, a difference in acidity across a thin membrane, is, in its essential physics, the very same kind of energy source that every living cell on Earth uses today to power itself. Right now, in every cell in your body, your metabolism is generating chemical fuel by exploiting a difference in acidity maintained across a membrane. It is the universal power mechanism of life. And the alkaline hydrothermal vent generates that exact kind of gradient, naturally, geologically, with no life present at all. Think about what that means. In the vent scenario, the first life did not have to invent its power supply. It did not have to evolve, from scratch, the elaborate machinery for capturing energy. It moved into a place where the planet itself was already running that machinery. The gradient was already there, maintained by geology, flowing steadily in the dark, a free and constant source of usable energy. Life, in this picture, did not light the fire. Life found a fire already burning and learned to warm itself by it. And later, when life eventually moved out of the vents and into the wider world, it carried that trick with it, the trick of living off a gradient across a membrane, and it has never stopped using it. The signature of the cradle, in this view, is stamped into every cell that has ever lived. I want you to go down there, into the dark, and feel it. Sink below the sunlit surface of the early ocean, down through the cold black water, all the way to the floor, to the base of one of these pale mineral towers. There is no light here. There has never been light here. There is nothing alive, not a single living thing, anywhere in this dark. And yet this place is not still, and it is not dead in the way a rock is dead. Warm fluid is seeping up through the honeycomb of the tower, through millions of tiny stone chambers. Across the thin wall of every one of those chambers, a gradient holds, a steady difference, a charged battery. Energy is flowing here, constantly, patiently, maintained by nothing but the planet's own heat and chemistry. The engine is running. It has been running, in the cold and the dark, since long before there was anything to use it. It is running, right now, waiting. And one day, in one of those countless small stone chambers, the chemistry gathered there will be of just the right kind, and it will begin, faintly, to use the gradient, to feed on the flow, to organize itself around the energy the dead planet has been offering freely all along. It is worth pausing on why scientists cannot simply settle this, why both the pond and the vent remain live candidates, rather than one having clearly won. Each setting solves part of the problem beautifully and leaves another part awkward. The warm little pond is excellent at the chemistry of building long molecules. Its cycles of drying force the building blocks together and drive the joining reactions, and it sits in sunlight, which is a generous source of energy, and it can concentrate things to a degree the open ocean never could. But the pond is also exposed and fragile. It can dry out completely and lose everything. It can be flooded and diluted. It is at the mercy of the weather of a chaotic young world. The deep vent has the opposite profile. It is stable, sheltered, and it offers that extraordinary free gift of a natural energy gradient. The very kind of gradient life still runs on. But the vent is awash in seawater, and getting building blocks to link into long chains while they are bathed in water is chemically difficult, the very problem the drying pond solves so well. So the honest situation is that the pond is good at the construction and weak on the energy and stability, while the vent is good at the energy and stability and weak on the construction. Each cradle has a gift the other lacks. This is why some scientists suspect the truth may not be a clean choice between the two at all. Perhaps the relevant chemistry happened across more than one kind of setting, the early stages favored in one environment and later stages in another, with the building blocks assembled in drying pools and then washed down, eventually, into vents where a steady energy supply could take over. Or perhaps there were settings we have not yet thought of, other places on that varied young planet where construction and energy and shelter happened to come together at once. The disagreement over the cradle is not a sign that the field is lost. It is a sign that the early Earth offered more than one promising nursery, and that the matter climbing toward life may have used whichever one it found itself in. Whichever cradle is the true one, the warm little pond with its patient cycles of sun and drying, or the deep vent with its steady inherited gradient, notice that the lesson is the same, and it is a humbling one. The first life did not build the conditions for its own existence. It did not create its energy source. It inherited one. The early Earth, the dead planet, was already running engines, already maintaining flows of energy, already cycling and gradient making, long before anything was alive to care. Life did not arrive and impose order on a passive, inert world. Life emerged because the world was already in motion, already pushing energy through matter, already, in a sense, halfway to the thing it would become. The cradle was warm before the child was ever in it. Part 11. The other stories we tell. Everything I have walked you through so far is the mainstream scientific picture, the converging account that most origin of life researchers are working within. But it would be dishonest to pretend it is the only story people tell about how life began, and it would be a missed opportunity because some of the alternative stories are genuinely worth examining, not to mock them, but to see clearly where each one is strong and where each one quietly falls apart. So let us walk through the other stories carefully and see what the data actually supports. The first alternative is the idea that life did not begin on Earth at all. This idea is called panspermia, and the word means, roughly, seeds everywhere. The proposal is that life, or its first crucial pieces, did not originate on our planet, but arrived here from somewhere else, carried across space on a comet, an asteroid, or a drifting grain of interplanetary dust, and then took root on the young Earth. Now, there is a strong version of this idea and a weak version, and the honest scientific assessment treats them very differently. The strong version says that fully living organisms, microbes, complete cells, travelled between worlds and seeded the Earth. And here we have to be clear. There is no evidence for this. None. We have never found a living organism that originated off the Earth. And there is a deeper problem with the strong version of panspermia, a logical one. Even if it were true, it would not actually answer our question. If life arrived here from Mars, or from some other star system, then we have not explained how life began. We have only explained how life moved. The question simply relocates to wherever the microbes came from, and the hard problem, dead matter becoming living matter, is exactly as unsolved as before. Strong panspermia does not solve the origin of life. It just changes its address. But there is a weak version of the idea, and the weak version is not fringe at all. It is mainstream chemistry, and it is well supported. The weak version says, not that life arrived from space, but that some of the raw ingredients did. And this is simply true. We have found complex organic molecules, including amino acids, on meteorites that have fallen to Earth. We have detected organic molecules, the chemical cousins of life's building blocks, in the gas and dust of star-forming regions across the galaxy. Space chemistry, it turns out, genuinely manufactures the building blocks of life, out there in the cold and the dark, with no planet and no life involved. And the early Earth, during the heavy bombardment of the Hadean, was being struck constantly by comets and asteroids and dust, all of which would have been delivering exactly this kind of organic material. So the weak version of panspermia is real, and it folds neatly into the mainstream story. It does not replace the account I have given you. It just adds a delivery service, topping up the early Earth's chemical kitchen with ingredients cooked in space. Panspermia, as aliens seeding us, is unsupported. Panspermia, as some of the ingredients having an extraterrestrial origin, is ordinary, accepted science. The second alternative story is the one that says the whole thing is simply too improbable to have happened by chance, and therefore must have been designed. This argument has real intuitive force. A living cell is staggeringly complex. The odds of all its parts coming together by random chance, the argument goes, are so small as to be effectively zero, smaller than the odds of a tornado sweeping through a junkyard and assembling a working airliner. And if random chance cannot do it, then something must have guided it, something must have designed it. The scientific response to this is not to dismiss it, but to point very precisely at the hidden assumption that makes the argument work, because the argument is built on a mistake. The mistake is the assumption that a complete modern cell had to assemble all at once in a single step from scattered random parts. And that is not what any origin of life scientist proposes. It is not what I have described to you tonight. Go back over the story we have actually walked through. The building blocks form on their own, readily, because that is just chemistry. The fatty acid vesicles assemble on their own, automatically, because physics in water leaves the molecules no other option. The RNA strands form, and then a blind selection, a pure physical filtering, favors the ones that are stable and that copy. Not one step in that chain is a wildly improbable leap. Each step is individually likely. Each step is something the physics and chemistry tend to do, and that completely changes the probability. An event that is fantastically improbable as a single, all-at-once leap becomes nearly inevitable when it is broken into a long sequence of individually probable steps and then given a whole planet's worth of chemistry to run on and hundreds of millions of years for it to run. The tornado in a junkyard image is a vivid one, but it describes a process no scientist believes in. It attacks a version of the origin of life that the actual science abandoned long ago. The real story is not one impossible jump. It is a long staircase of small, ordinary steps, and a staircase can take you to a height that no single jump ever could. There is a third version of the alternative stories, a more modern one, and it points at the laboratory. It looks at the genuine achievements of synthetic biology, scientists building artificial cells, engineering self-copying RNA, and it draws one of two conclusions. Either, it says, this proves life needs intelligent engineering to come about, since look, it takes brilliant scientists to do it. Or, in a more conspiratorial form, it claims that scientists have already secretly created life from scratch and are concealing it. Both of these misread what is actually happening in those laboratories. The synthetic biology achievements, remarkable as they are, almost all begin with the machinery of existing life. They modify it, they reprogram it, they build with parts that life already invented. That is an extraordinary feat of engineering, but it is not the origin of life question. The origin of life question is whether you can get a living system from pure, non-living chemistry, and the honest answer is that no laboratory has yet done it. That is not a cover-up. It is the openly stated frontier of the field. The scientists working on this will tell you plainly that the full gap has not been closed. And that brings us to one more piece of evidence, a hard number, that sharpens the whole picture and tightens the timeline more than you might expect. Every living thing on Earth today, every bacterium, every redwood, every person, is descended from a single common ancestor. We call it LUCA, the last universal common ancestor. LUCA is not the first life. It is the most recent organism from which all currently living things descend, the trunk from which every branch of the tree of life grows. And by comparing the genomes of living things and counting the slow accumulation of differences, scientists can estimate when Luca lived. A major study, published in 2024, placed Luca at roughly 4.2 billion years ago. Sit with that date for a moment, because it is startling. The Earth itself is only about 4.5 billion years old, and the heavy, sterilizing bombardment of the Hadean made the planet uninhabitable for a stretch of its early history. To find that the common ancestor of everything alive was already here 4.2 billion years ago means life appeared almost shockingly fast, almost as soon as the planet could possibly hold it. And the same study found something else striking. Luca was not a simple thing. Luca was already a complex organism with a substantial genome, thousands of genes, the full apparatus of a sophisticated cell, apparently already living as part of an ecosystem. Luca was not the beginning. Luca was already an advanced product of evolution. And that means the genuinely first life, the simple protocells, the RNA world ancestors of Luca, had to come earlier still and had to get from raw chemistry all the way to a working cell in a remarkably short window, just a few 100 million years after the planet became habitable. Now, you might think that makes the origin of life look harder, more rushed, more improbable. But turn it around. If life appeared almost the instant the Earth was capable of supporting it, then life is probably not a slow, freakish accident that the universe stumbles into once in a great while. Life that appears that fast, that eagerly, the moment conditions allow, looks far more like what the thermodynamics predicted. It looks like something matter does readily, reliably, whenever it gets the chance. The speed of life's appearance is not evidence that we were lucky. It is evidence that we were, in some deep sense, expected. Part 12. There was never a line. We have come a long way down, you and I. We started this journey at the top, at the scale of the redwood and the boulder, with that bright, certain, lifelong conviction that living and non-living are two separate kingdoms, divided by an absolute wall. And then we began to walk down. Down from the organism to the cell, down from the cell to the molecules, down from the molecules to single chemical reactions in the dark water of a young world. And somewhere along that descent, if you have been feeling it, the wall we set out to find has quietly stopped looking like a wall. Let me gather the whole journey into one continuous line, because seen all at once, it is genuinely something to behold. It begins with raw chemistry. A young planet, its oceans stocked with building blocks, some formed in place, some delivered from space, sugars and nuclear bases and amino acids and fatty acids, all of it ordinary, all of it the product of dead chemistry and raw energy, all of it proven to assemble on its own. Then self-organization takes over. The fatty acids fold themselves into vesicles, into boxes, because the physics of water leaves them no choice. The nuclear bases and sugars link into strands of RNA, and a blind physical selection begins to favor the strands that are stable and that copy. The double agent, RNA, message and machine at once, quietly dissolves the chicken and egg paradox that once looked like a locked door. And then the box closes around the strand, the protocell forms, and for the first time, the two requirements of life, a self-replicating molecule and a bounded space for a metabolism, exist together in one package. And the whole climb is framed, from bottom to top, by thermodynamics, by the realization that this is not matter rebelling against the universe, but matter serving it, dissipating energy, producing entropy, doing exactly what the second law favors, wherever the energy flows strongly enough, step after step after step, and not one of those steps required a miracle. Each one required only physics, chemistry, water, energy, and time. It is a magnificent story. It is detailed, it is grounded, it is supported at every stage by experiment. And now I have to tell you the most honest and the most important thing in this entire video. That story is not finished. The single most central thing has not actually been done because for all of it, for all the steps we can demonstrate, no laboratory on Earth has ever closed the full gap. No one has ever taken non-living chemistry and run it, start to finish, all the way through to a system that everyone agrees is alive. We can show you the building blocks forming. We can show you the vesicles assembling. We can show you RNA copying itself. We can show you, in piece after piece, every section of the path lit up and demonstrated. And still, no one has walked the entire path in one continuous journey and arrived at the far end holding something undeniably alive. We have lit every stretch of the road and we still have not made the whole trip. So what, exactly, is the mystery that remains? It is worth being precise about this, because the mystery is not where you might think. The mystery is not where the ingredients came from. We have a strong answer to that. The mystery is not what the first self-replicating molecule was. RNA is a powerful and well-supported answer to that. The mystery that genuinely remains, the true core of the question how did life actually start, is the transition itself. It is the precise nature of the crossing. It is the question of how and where and in what exact moment a collection of chemicals that is merely reacting becomes a system that is genuinely living. And here is the deepest possibility this video has been walking toward all along, the one I want to leave you sitting with in the dark. It may be that the reason no one can point to the moment of crossing is that there was no moment. It may be that the reason we cannot find the line is that there is no line. Go back one last time to where we began, to that confident intuition that alive and not alive are two separate boxes, two distinct kingdoms, and that every object in the universe belongs cleanly to one or the other. Everything we have seen tonight has been quietly eroding that intuition. The virus, with its instructions and no machinery, sitting in the gap. The fatty acid vesicle, growing and dividing and feeding, doing a faint sketch of life with no genes at all. The RNA strand, copying itself, evolving, with no cell around it. The protocell, with both of life's components, but with no one able to say for certain whether it is alive. At every stage, we have found not a wall, but a slope, not a border, but a gradient, not a sudden bright line, but a long, smooth, continuous shading from the plainly dead to the plainly alive, with every intermediate degree filled in. And if that is the true shape of it, then alive is not a category that matter is in or out of. Alive is something matter does, by degrees, more and more fully. And now, finally, we can return to the image I asked you to hold on to, all the way back near the beginning. I asked you to remember the fire. A fire moves, and grows, and consumes, and spreads, and yet a fire is not alive. And the reason a fire is not alive is instructive, but so is the deeper thing the fire shows us. A fire is not an object at all. A fire is a process. A flame is not a thing that exists, it is a thing that happens, a reaction sustaining itself by continuously consuming, persisting only as long as it keeps going. You cannot hold a fire still. You cannot find the single instant a fire begins, the precise frame where not fire becomes fire. There is only a smooth, quickening chemistry going faster and faster until at some point, without any line ever being crossed, there is plainly a flame. Life may be exactly like that, not a thing that matter is, but a process that matter does. Not a substance, but a reaction, sustaining itself by continuously consuming, persisting only as long as it keeps going. And if life is a process and not a thing, then asking for the precise moment life began is like asking for the precise moment a fire began, or the precise moment a river became a river, rather than 1,000 trickling streams, or the precise moment a pile of sand became a dune. The question assumes a sharp line in something that has no sharp lines. There was no instant of crossing. There was only chemistry, on a young and patient planet, getting slowly, steadily, relentlessly better at the business of continuing itself, better at copying, better at concentrating, better at riding the flow of energy and dumping the disorder outward. And it kept getting better, by tiny degrees, with no single dramatic moment anywhere in it, until one day, without any line ever having been crossed, that chemistry had been alive for a very long time. So here, at the end, is the answer to the question we began with, and it is stranger and gentler than the question expected. How did life actually start? It started the way a fire starts, the way a dune builds, the way a dawn arrives. Not with a switch thrown, not with a spark of vitality entering dead matter, not with a single miraculous instant. It started as a slow quickening of ordinary chemistry, on an ordinary world, doing exactly what the laws of physics, given energy and matter and time, incline it to do. And that should change how you feel, lying there in the dark, listening to this. You have probably always carried, somewhere underneath your thoughts, the quiet sense that you are a thing apart, a spark of life that was somehow placed into a universe of dead matter, a brief flame of being against an inert and indifferent cosmos. But the physics tells a different story, and it is, I think, a far more astonishing one. You are not a thing that was placed into dead matter. You are something that dead matter has been doing, continuously, without a single pause, for nearly 4 billion years. The same atoms that drift in the rock and the sea and the air fell, long ago, into a pattern that could continue itself, and that pattern has been flowing forward, unbroken, ever since, through every ancestor, all the way down to the particular arrangement of it that is listening to these words right now. There is one more thing I want to leave with you before the dark settles in fully, because it follows directly from everything we have walked through, and it is the gentlest possible place to end. If life is not a freak accident, but a thing that ordinary matter does, reliably, whenever it finds itself in a strong enough flow of energy, with the right materials and enough time, then the question of how life began on Earth quietly becomes a question about the whole universe. Because the conditions that produced us were not special to this planet. Energy flows through matter everywhere. Stars pour it out. Planets generate it in their hot interiors. The same carbon that builds us is among the most abundant elements in the cosmos. The same physics of bonding, the same tendency of certain molecules to self-assemble in water, the same thermodynamics that favors energy-dissipating structures, all of it is universal. None of it is a local accident of one small world. If matter became life here, by no miracle, through nothing but the ordinary working out of physical law, then there is no obvious reason the same slow quickening could not be happening, or have happened, in countless other warm and ancient seas, around countless other stars. We do not know that it has. But the story we have told tonight does not describe a one-time event. It describes a process. And processes, unlike miracles, tend to repeat. The boulder and the redwood were never in two separate kingdoms. They were always made of the same thing. The only difference is that one of them is matter, sitting still, and the other is matter that once, in a warm and ancient sea, began to move in a way that has never yet stopped. You are the second kind. You always have been. And the strangest, quietest fact in all of science is that nobody, anywhere, can tell you the moment it began.